Hello students, welcome to Marine Engineering Tutorials. I am Atul Kumar Gupta and back with a new tutorial. Presently, we are studying marine auxiliary systems and deck machinery. Today, we will discuss the following topics about oil purification in disk type oil separators. In this tutorial, we will first learn about the disk type purifier bowl. Next, we will understand the selection of gravity disk. Then, we will explore the action of particles between the disks. Finally, we will study the factors affecting particle size. Let's go through these topics in the following slides. Disk type purifier bowl. The sketch shows a disk type oil separator which can retain more sludge due to its wide bowl and is easier to clean. These separators operate at a maximum speed of 7500 rpm. Purifier assembly sequence. The purifier bowl is mounted on a vertical shaft driven by an electric motor through a friction clutch. An oil distributor is centrally placed inside the bowl. It supplies dirty oil for purification through the distribution holes. A stack of up to 150 conical discs spaced 2 to 4 mm apart is mounted on the oil distributor. These discs provide extended settling surfaces where heavier impurities settle beneath the disc surfaces. A top disc is placed above the disc stack, forming the clean oil outlet. The purifier bowl is closed with a bowl hood which is secured in place using a ring nut. A gravity disc is attached to the bowl hood. It determines the position of the oil-water interface during operation. Operation of purifier and estimation of oil-water interface position. When the bowl reaches its rated speed, sealing water is introduced through the central passage until it overflows from the high phase outlet. When dirty oil is admitted, it displaces some of the sealing water, establishing the oil-water interface. The oil then enters the disc stack through the distribution holes, flows between the discs, and the clean oil exits through the light phase outlet. The separation force is weakest near the center, and water or solid particles must travel a greater distance to reach the bowl wall. Heavy particles, upon striking the disc surfaces, accumulate and slide along the disc toward the periphery, while lighter particles move upward towards the bowl center. I is the distance of the oil-water interface from the bowl center line. L is the distance of light phase boundary, that is oil, from the center line. H is the distance of the heavy phase boundary, there is water from the center line. R1 is the inner radius of disk from the center line. R2 is the outer radius of the disk from center line. Average disk radius R is equal to R1 plus R2 divided by 2. Equilibrium equation for interface position. In equilibrium, omega square R rho naught into bracket I square minus L square is equal to omega square R rho W in bracket I square minus H square. Simplifying it, we get rho W by rho O is equal to I square minus L square divided by I square minus H square. This formula is used to determine the position of oil-water interface. For correct operation, the interface must remain within specific limits, that is, between the distribution holes of the disk stack. If the interface moves inward, water will be discharged along with the clean oil. If the interface moves outward, oil will be discharged with the water. In clarification mode, no water seal is required. Clarified discs either have no distribution holes or the bottom disc alone is without holes. In fact, purified discs can also be used for clarification. Selection of gravity disk. The change in density of oil will disturb the position of interface. Position of interface is adjusted by selection of correct gravity disk. It is important to know that change in oil temperature causes changes in specific gravity. Thus, separating temperature must remain constant. The oil feed rate in a purifier should be optimized for best performance. Feed rate should be adjusted to provide 5% above the actual fuel oil consumption so that fuel oil level in the service tank is steadily maintained. Usually, a nomograph, as shown in the sketch, is provided by the manufacturer which specifies specific gravities of oil on the ordinate. Oil temperature in degrees Celsius on the FCSA. Inner diameter of gravity disk in millimeter on the ordinate. Required feed rate in liters per hour. As an example, gravity disk size is calculated on the basis of specific gravity of oil given as 0.95 at 50 degrees Celsius, separation temperature of 98 degrees Celsius, and feed rate of 3000 liters per hour. First of all, the point B for specific gravity of 0.95 at 50 degrees Celsius is obtained by extending specific gravity arc along AB and temperature line along CB, both upwards. Thereafter, point B is extended parallel to downward specific gravity arc along BE until it meets E with temperature line DE at 98 degrees Celsius extended upwards. Point F is marked on the feed rate line to select feed rate as 3000 liters per hour. Join EF, which cuts gravity disk ID line and gives 571.5 as the approximate size. Now the purifier is set up with a gravity disk of the next higher size, which is 75 mm. If the purifier operates without an overflow, the disk size is correct. Otherwise, it should be changed to 71.5 mm. As seen from the nomograph, an increase in the specific gravity of oil requires a reduction in gravity disk size. Increasing the specific gravity of the oil tends to push the oil-water interface outward, potentially causing overflow from the heavy phase outlet until equilibrium is reestablished. If the interface shifts too far and breaches the water seal, oil will be discharged from the heavy phase outlet, triggering an alarm. Ideally, the interface should lie just over the distribution holes. Conversely, reducing the specific gravity of oil will shift the interface inward towards the axis. This reduces the centrifugal force acting on the mixture, lowering separation efficiency and potentially allowing contaminants and water to carry over with the light phase outlet. Gravity disks are interchangeable on most purifiers. Their center bore size is selected based on the specific gravity of oil being centrifuged. The largest possible bore should be used, provided it does not risk causing overflow. Action of particles between the disks. This sketch shows the movement of particles between the disks. Oil flows in a streamlined manner between the two disks, with the velocity of oil particles being zero near the disk surfaces and maximum at the center. In a centrifuge, the oil flow between the disks is radially inward and then directed upward towards the clean oil outlet. Contaminants tend to settle on the underside of the disks where the velocity is minimal. These particles are then forced outward by the centrifugal action into the sludge space of the bowl. The limit particle path defines the smallest particle size that can be effectively removed by the centrifuge. Particles smaller than this limit will pass oil out with the clean oil. Factors affecting particle size. Following factors are responsible that affect the particle size in the clean oil outlet. Viscosity. Viscosity plays an important role. Higher viscosity increases the drag on particles, reducing separation efficiency. Therefore, oil should be preheated to the highest practicable temperature to lower its viscosity. Disc spacing. Smaller disc spacing increases the surface area and promotes separation by maintaining laminar flow. Disc spacing is usually between 1 to 2 millimeter. Disc diameter. Larger disc diameters increase surface area, centrifugal force, and dwell time of oil between the discs, improving separation. However, disc diameters are typically limited to about 400 millimeter to restrict bowl size. Disc inclination. Inclination of the disc to the vertical increases the surface area and helps reduce bowl width. Thus, usual inclination is about 45 degree. Higher inclination angles may increase particle size without improving separation. Speed of rotation. High rotational speed increases centrifugal force and improves separation. Typical operating speeds range from 5000 to 8000 rpm. Throughput or oil feed rate. Lower throughput results in a smaller particle size limit, producing cleaner discharge oil. Higher throughput increases the limit particle size. Throughput is also influenced by water content. If the oil contains a significant amount of water, throughput must be increased to remove it effectively. This completes our study of the disc type purifier bowl, the selection of gravity disc, the action of particles between the discs, and the factors affecting particle size. This book has been written by me and covers all the topics as per the syllabus specified by the Indian Maritime University. It explains the concepts with simple illustrations and provides answers to all the questions that have appeared in the examination conducted by the Indian Maritime University. This book will help students prepare for the exam and also assist them in working safely with shipboard auxiliary systems and deck machinery. I hope you enjoyed the lecture. Feel free to share your feedback in the comment box. If you found the tutorial helpful, you may share it with your friends. You can also subscribe to the channel to receive notifications about upcoming tutorials. I will be back soon with another lecture. Thank you for watching till the end.